internal energy. And it's just what it says. It's the energy on the inside, and we can denote this with a capital E. And it's just what it says, okay? It's all the energy inside of something. But that's not an easy thing to quantify. So this is the sum of the kinetic and potential. Sum of the kinetic and the potential energies in a system. And I'm just going to tell you right now, that's not only difficult to measure, it's basically next to impossible. Why would that be next to impossible to measure? Internal energy. Two guys.
Because like if an object heats up, it has more energy at that point, it can cool down.
Okay, so there's some changing going on. But what if we could take a snapshot in time and just say, okay, what's the internal energy right now? Why is that an impossible thing to measure?
You don't know exactly how much potential energy it has.
Okay.
Energy is going to be coming in and out of the system constantly.
Let's say we can isolate the system in a perfect, let's say we could do that, even though it's not real, right? It still would be impossible to. And I think you're starting to get close to it, okay? The reason is you would have to know the position and motion of every single particle in the system. Think about that. That's the only way that you could figure out the kinetic and potential energies, right? Because remember, potential energy is positioned in the system. So wouldn't I have to know all the positions? And kinetic energy, I'd have to know the motion of it, right? Because in order to know the kinetic energy, I got to know all the motions. Do you think you can know the motions and the positions of all the atoms in a system? And their electrons and all that stuff? No, you can't. Right? It's too much information to quantify, even for something very small. So we could say, this is impossible to measure. But we can still entertain it as a concept. You know, there is a finite amount of energy inside of matter. Impossible to measure. But changes in internal energy can be measured. I'll tell you honestly, and I mean this, it's something I take pride in. And I talked to my wife about this, because this doesn't just extend to teaching, but like, my mind works with analogies. That's the way my mind works. I can always say this is like that. And I have a better understanding of things when I can put it in that context. And then I'm even happier when I can come up with something that can make something like this more clear to my students. So I'm telling you there's this concept, internal energy, the sum of all the kinetic and potential energies. That's not a difficult concept, is it? You take kinetic energy, you take potential energy, you add it all up, right? And I'm telling you the problem is you can't really measure that because it's impossible to get that much information. It's possible to know all the positions and locations of all the particles in a system. But then I tell you that you can measure changes though. And here's an analogy I got, and I think it's a great analogy. Imagine I have a bottomless pool. I don't know how deep the pool is. It could go on for hundreds of feet, thousands of feet, infinity. I really just don't know. Okay? I don't know how deep it is. So I could never ever stand here and tell you the volume of that pool. Right? I could never tell you that. Because I don't know how deep the pool is. Just like I can never tell you how much kinetic and potential energy are in a system. I don't have the way to gather that information. But let's say in my pool, my pool up at the top few feet is kind of cubic in nature. So like I can see the top of the water here in my pool. Follow me? I don't know how deep it goes, but I know the length and the width of the pool, and I can measure how much this goes up and down. If I can measure that, I can measure the change in volume. Because if I know the length, the width times the height, and then the length, width times the height, I can figure out what the difference is. So even though I don't know what the actual amount is, I can tell you the change though. Does that make sense? I can have a bottomless pool and tell you how much the volume changes. I just can't say how much volume was in there to begin with. Because all I'm measuring is how much this goes up and down. And if I know it goes up, say this much, let's say that's the difference there. Well, I have a height, I have a length, I have a width. Length times width times height, that's a volume. I get a change in volume. Okay. All right, so we can measure changes in internal energy. And you remember deltas mean change? We've had that before, right? Okay. So this is going to be delta E equals, and here's a new letter, Q plus W. Q plus W. Some textbooks use a capital Q, so if you see a capital Q, Q is always basically the same thing. This is change in internal energy. Q is heat, and W is work. Okay, so when you look at this, you're like, well, where did that come from? Well, this is kind of doing like a specialized look at kinetic and potential energy. Remember we said internal energy is the sum of kinetic and potential? Guess what work is a form of?
Potential energy?
No? Kinetic. Because it applies that a force was applied over a distance, so there has to be distance going on. Heat is a form of energy which has the ability to do work. So that's a form of what? Potential. Okay. So really this is just written in a specified way that we can say changes in internal energy can be related to the sum of the kinetic portion and the potential portion. Okay, now these things are measured in joules or kilojoules. Joules or kilojoules. These are going to be joules or kilojoules. So those are our units that we'll typically use here. Okay, so this is, say, form of potential energy. So form of potential energy. And this is a form of kinetic energy. Come on, this. Okay, so here's the trick here. That is obviously not a very difficult equation, is it? No. Okay. Here's the deal, though. You got to watch your signs. This is what this is the first time I'm probably going to say it this chapter, and this will probably not be the last. You got to watch your signs. Signs are huge here. Okay. So, for instance, okay, if I say that I give you 4 oranges, you know that's a positive. And if I take an orange from you, you know you subtract an orange and now you have 3. Okay, that's a very simple concept because you're talking about concrete items, okay? With energy, remember that you're not creating or destroying energy. So you got to keep track of where the energy is going. And again, we said as chemists, we take the science point of view of the system. So whatever it is we're studying, we're going to take that thing's point of view. So if that thing gains energy, we're going to say it's positive. And if that thing that we're studying loses energy, we're going to say it's negative. Whereas physicists might look at it different. They might say, I'm more interested in the effects on the surroundings. And then they would call that positive. Okay? So it's a matter of perspective. So for our purposes, positive values are going to be when we're dealing with endothermic things. Because what's endothermic mean? Energy goes. Yep. So this is when energy flows into the system. And what would we call it when energy flows out? Exothermic. Energy flows out. System. And I, you know, to be fair, I'm being a little loose with my terminology here. Actually, if I just want to talk about energy flowing in or out, I should be saying endo or exogonic. Okay, exergonic or exergonic or endogonic. Endothermic, exothermic means specifically heat flows in and out of the system. Okay, I'm not trying to be tricky here. And just, you know, it's just a subtlety in terminology. Okay, so let's do an example of this example. So let's say calculate the change in internal energy. Calculate the change in internal energy. Calculate the change in internal energy. In a system that does 3.3 kilojoules of work on the surroundings while absorbing 2.9 kilojoules as heat. Okay. So it says calculate internal the change in internal energy. So that's delta E equals, I don't know. That's what I'm looking for. It's a change in internal energy. And secondly, they tell me that we're doing some work here. Work, and they say is 3.3 kilojoules. Anybody want to add anything at this point?
Is it changed to joules?
No?
Q is 2.9.
No? Before that,
Negative.
this has to be a negative. See where I'm saying you got to watch signs? It doesn't tell you a negative. What it's telling you is that the system did work on the surroundings. Yeah. Well, thank you, sir. Anybody see Adam's shirt, by the way? Wow. Did you get to sleep in?
No.
That sucks. I was kind of hoping that was the case. Never mind. Okay, now think about this now. We've done work on the surroundings. Okay, let's say you're a system. You are, think about it this way, you're a system. And let's say you do some work. What happened to your amount of energy? You lost some. Right? So try and think about things that make sense. Because you like when you just say a system does work, you're like, what the heck does that mean? You define a system. Well, what if it's you? And you do work. You lose energy, right? But you can also gain heat as you do that. Right? Some things can be, energy could be coming in.
So you can't, if you can't destroy or create energy, say you're like pushing a rock or something, the energy like goes through your like legs and arms, I guess. Where does it go after that?
So you've spent some energy to move the object, right? So some of that energy went into physically moving the object. A lot of it went into friction and heat.
So it just like goes off into the air.
It goes off into space,
and
yeah.
it gets reused.
Yeah, well, not reused, it just diffuses. And then what happens to it after then? Who knows? It might be transformed in some way or another, who knows? But it's still gonna be there. Okay. So Q, if the system absorbs heat, what's the sign for that? Plus. And I would get in the habit, and this is up to you, but I would be in the habit of putting a sign every single time. I wouldn't be just putting signs in when it's negative. because then it's too easy to make a mistake. But if you're putting in a sign every time you're talking about this directional heat energy and stuff like that, then you've said to yourself, I've taken the time to think this through, and this is the sign. Okay? So we have an equation that says delta E equals Q plus W, or delta E equals positive 2.9 kilojoules plus a negative 3.3 kilojoules, or delta E is equal to negative 0.4 kilojoules. So we can say the system lost energy. Okay. Okay. Now, back to this thing. What was work? What is work?
Energy over distance.
Okay, so force applied over work equals force times distance. So force applied times a distance. Okay. So remember here in internal energy, I said it's the sum of kinetic and potential energies. Remember that? And we said that heat could be like potential and work could be like kinetic. Follow me? Okay. Well, now let's think about a force over distance like this. Work equals negative pressure times change in volume. This will be the next thing. So a pressure is a force. And a distance can be related to a change in volume, because a change in volume means a change in work. So think about it like this. Something that most of you guys use most days now. In your car, you have this thing called a piston, right? And in this piston goes up and down in here. And what you do is you inject gas into there, and that piston comes up and compresses everything, and then you have a little spark plug here that ignites a spark, which makes this thing explode and go down. Make sense? So there is a change in volume that takes place when that thing goes up and down. And that change in volume is working against the pressure, and the pressure it's working against is the atmospheric pressure. When this thing pushes down, it's pushing against the atmosphere. And that tells us how much work we get out of it. So that's something applicable to a race car kind of guy. Right? So we can talk about a particular type of work called pressure volume work. And the reason that this is important for what we're talking about is because in a lot of chemical reactions, you got things that are expanding into the gaseous state. Like we just got done talking about gases. If gases expand, they're going to do some work by changing volume. So we can say work equals negative P times delta V. Oops. Now again, watching signs, why is there a negative in there? The negative is in there so it makes sure it stays from the point of view of the system. If I was taking the point of view of the surroundings, I would take the negative sign out. So again, this thing, that negative is there for directional purposes. It's not like there's no such thing as negative pressure. It's just, this is telling us direction. Okay? So this is going to be measured in ATM. Let's see. Changes in volumes are going to be measured in liters. And so this thing is measured in liter atmospheres. And that might look familiar because that's part of our gas constant, isn't it? Your atmosphere over Kelvin mole. And so this is kind of part of it. And we can say that's true where delta V, what would delta V be equal to? Should be able to figure this out.
Negative P times.
No, I'm not saying rearrange it. What's delta V by itself? Okay, which would be?
Like, what's the unit?
No, like what would the variables would be? So, Pat?
The original volume minus the volume.
Other way around. So volume final minus volume initial. And again, that's important because of sign reasons. So you got to make sure you get that right too. So again, I keep telling you these sign reasons. So let's see. So we can say work equals negative P times volume final minus volume initial. Okay, so that'd be the sum of it. And one other thing you got is a conversion factor here. 1 liter atmosphere. 1 liter atmosphere is equal to 101.3 joules. And if you look at that, that has to do with like KPA. Yep.
Can I use your
Yep, absolutely. Remember KPA is 101.325? So this is no coincidence. Okay, so that's just a conversion factor there. Okay, let's do an example of this and then we can pretty much probably be done because nothing else to do. Okay, so let's see, here's an example. The volume of a balloon, the volume of a balloon. Again, balloons because they're easy because you can expand and contract them. And 2 L's, 2 O's?
Yeah.
Who knows?
Yeah, who knows such things? Changes from 5.0 liters to 4.6 liters by losing 100 joules as heat. This change occurs under a pressure of 0.91 ATM. Calculate the change in internal energy. Okay. So again, take one thing at a time, watch your signs, okay? So the first thing I get is the volume of a balloon changes. So I know I'm getting some volumes coming. And it says it goes from 5.0 liters. So which volume is that? The initial. Okay, so volume initial is equal to 5.0 liters. And it's changing to 4.6, so obviously that's what? Is what? Well, I'm just saying it's changing to what volume? Volume final. Okay. Now that's 4.6 liters because that is a volume, but we have an equation that will bring in that sign. Okay. What do we say about losing 100 joules as heat? What letter are we talking about first? What letter is heat? Q. And then what am I going to put in for Q? Negative 100. Okay. Change occurs under a pressure of 0.91 atmospheres. Well, pressure equals 0.91 ATM. And calculate the change in internal energy. So I want delta E equals. So there I've got all my things I need. Now for delta E, what do I need? Oh, go ahead.
Why is pressure like positive?
Pressure is always going to be positive, but it comes out negative when we put it in the equation.
Oh, okay.
Right, so it's gonna. The signs of what we got to really watch are: is heat going in or out? is work being done on or by the system. As far as the changes in volumes and the changes in pressures, those things are just going to be positive numbers, but when you put them in the equations, there's signs in there to adjust for them.
So if it said, if it was 4.6 to 5, would one of them be negative?
Yep.
Would it be the 5 would be negative?
Well, no, it's not going to be negative because look, it's going to come out in this equation right here. That's going to adjust and give you the positive and negative sign as needed. So what I'm saying is this, the time you really got to watch signs in particular is when you're talking about these things. Heat and work. Oops. Because we got to tell what direction the heat's going. Okay, so let's come here. Now, all right, I want to know delta E. What kind of things do I need to know delta E? I need to know, Jacob? Work and heat. Do I have either of them?
You have, what, heat?
We got heat, but we don't have work yet, right? So maybe we should go get work first. Well, what's work equal to? Work is equal to negative P delta V. So work is equal to negative, well, we have a P, 0.91 atmospheres. And delta V, that's going to be final minus initial, right? Final minus initial. So what's my final? 4.6 liters minus 5.0 liters. So that actually comes out to be a funky number there. Let's just do it step by step. So that's going to be 4.6 minus 5.0, negative 0.4. Work equals negative 0.91 ATM times negative 0.4 liters. So work is going to come out to be positive, and that's going to be negative 0.4 times negative 0.91, and I get 0.364 liter atmospheres. Are you with me there? So just as a little side note here, okay, this thing's working against a constant pressure. Follow me? And what happened to the volume? The volume got smaller. Follow again. So what happened? The balloon got crushed down some, right? Wouldn't that involve the outside world pushing on the balloon? Follow me? So that work would be positive. The work's being done on the system. For negative, it'd be flowing out of the system. Well, that's why this comes out positive. So if you can envision those things, that's good. Now the problem is that in my delta E equation, delta E, I need everything in terms of joules. And this is terms of liter atmospheres. So I can get rid of liter atmospheres and go to joules, and that's what, 101.3 joules per 1 liter atmosphere, and I get 36.9 joules. Again, that's positive. That's going to be work. You can bring that back up here. Delta E equals Q plus W, or delta E equals, well, Q we said was negative 100 joules, plus W, and we said that was positive 36.9. So delta E is equal to negative 63.1, negative 63.1 joules. So that would be my final answer there. So do you see they look like simple problems, but do you see how they can be deceiving with signs and that? So I strongly suggest you do the homework, and you will get used to this quicker than waiting until later.
So are they always going to ask for delta E or?
Not necessarily.
Okay.
Yeah, not necessarily. I could ask you for work. I could ask you for Q. I could ask you for internal energy. Okay. All right. So really, that's all I got for you today. I was going to spend some time going over